This is sections 2.6 and 2.7 of Honors Algebra 2, Algebraic Theorems and Proofs. Yes! So we've done proofs and theorems in geometry class or Honors Geometry class last year, but we can do theorems and proofs in any math class, and everything we do in algebra at some point needs to be proven so that we know that it actually works and why it works, because it doesn't just come out of nowhere. And we can see by doing these things that all of math is very logically straightforward, and that if we change one thing, it's going to change everything about what we're doing. And so we need to understand the structure behind all of what we're going to be doing in algebra. And that begins with these definitions. An axiom is a statement that we assume to be true without proof. A statement that we assume to be true without proof. An axiom is also called a postulate. So axiom and postulate are synonyms, they mean the same thing. They're statements that we assume to be true without proof. We have to assume something, and then we can prove other things from that assumption. But we have to start somewhere, with some assumption. A hypothesis is a statement that is given, and a conclusion is a statement that follows logically from the hypothesis, from the givens or the assumptions. So the hypothesis is what we start with, the conclusion is the statement we reach at the end. And the process we go through to get from the hypothesis to the conclusion, that method of logical reasoning is called a proof. So proof is the logical reasoning from a hypothesis to a conclusion, with logical steps in between. A theorem is the statement that can be proven. A theorem is not something we hope can be proven. It's something that can actually be proven. A converse to a statement is a statement that's formed by interchanging the hypothesis and the conclusion. If you swap the hypothesis and the conclusion, if you reverse the order of the statement, the conditional statement, that's the converse. Now, if the original statement is true, that does not necessarily make the converse true. And we can show that something is not true by providing a counterexample. A counterexample is a single numerical example that makes a statement false. So in order to show that something is true, we have to prove it. In order to show that something is false, all we have to do is provide one counterexample. So you might want to pause the video until you get all of those definitions written down, and then continue. Here's an example of an algebraic proof. I'm calling them algebraic proofs because they deal with properties of algebra. They're going to deal with the algebraic operations, and will therefore look a little bit different from the proofs we did in geometry, though the structure is essentially the same. So here we're proving that for all real numbers a, b, and c, so they're not variables, they're fixed numbers, if a plus c equals b plus c, then a equals b. If a plus c equals b plus c, then a equals b. This is what we're proving. If we have that, that's our hypothesis, then it must be true that a equals b. So we look at that and we think, okay, we just subtract c from both sides. Well, this proof is telling us that we can do that. Okay, that we can take off the same number from both sides and we'll still end up with an equation, a valid equation. So that's what we're going to be proving. And just like in geometry, we start with what we're given. So statement number one is, well, a, b, and c are real numbers. They have to be real numbers and not imaginary numbers. And we start with our hypothesis. A plus c equals b plus c. What's the reason for that? Well, we were given that information, or it was our hypothesis. Step number two. We want to be able to say that we can subtract c from both sides. Subtraction is really addition in disguise, right? Subtraction is addition of a negative number. So if I want to subtract c, what I'm actually doing is adding negative c to both sides. So I need to add negative c to both sides. A plus c plus a negative c equals b plus c plus a negative c. Now what tells me that I can do that? That I can add the same number to both sides. So if you remember, that is called the addition property of equality. Addition POE. It says we can add the same number to both sides. We're kind of assuming that negative c is a number. We could actually show that, and we could state that as a separate statement, but I'm allowing us to skip that step. We're assuming that negative c is a number if c is a number. And it is. Okay. Now, we need to group together c and negative c. Because really, we were taking a plus c and b plus c, and we were adding negative c to those quantities, those sums. So now what I need to do in step number 3 is say, I can do c plus negative c before I add a. And I can do c plus negative c before I add b. What tells me I can do that? That I can associate these different values. That is the associative property. In this case, the property of addition. Okay, now that I've associated c and negative c, I can actually add them together. And c plus negative c is 0. There is a property that says that. So we've gotten that a plus 0 equals b plus 0. And that property that tells us that c plus its opposite is 0 is called the property of opposites. And we had a property that says anytime we add 0 to a real number, we just get back that real number. So a must equal b. A plus 0 is a, and b plus 0 is b. So twice there we are applying the identity property of addition, or the additive identity property. Says that the identity of addition is 0, and if I add that identity to a real number, I just get back the real number that I had before. So that is the end of our proof. We showed what we wanted to show, that a equaled b. So that very simple idea we have of being able to subtract the same number from both sides of an equation is what we've just proven. That is called the cancellation property of addition. So we just proved this, that for all real numbers a, b, and c, if a plus c equals b plus c, then a equals b. We could have just as easily proven the second statement there, if c plus a equals c plus b, then a equals b, just by performing the commutative property of addition in order to switch the order around. So we proved there the cancellation property of addition. In your immediate practice problem, you're going to prove the cancellation property of multiplication, which will work very, very similarly. A second example, prove the multiplicative property of 0. The multiplicative property of 0 says that for every real number a is some real number, a could even be 0 itself. If I take a times 0, I get 0. And if I take 0 times a, I get 0. So a real number times 0 is 0. We've assumed that to be true since probably 3rd grade when we started doing multiplication. But let's actually see why that's true. So our first statement is, well, we must have a real number. Let's call a real number. So we just start with that real number. That's all we have. Okay? So what do we do from there? Well, we are involving zeros, so what do we know about 0? We know that 0 plus 0 equals 0. because 0 is a real number, and when I add any real number to 0, I just get back the original real number. That property is the identity property of addition that we just applied in the previous proof. If I think of this 0 as just any real number, if I add any real number to 0, I get back the first real number. So that's all we're doing here. We're just taking that real number to be 0 itself. Now I've got a statement that involves zeros, an equation that involves zeros. I want to incorporate a into this equation. So I know I can add a to both sides, but I also know that I can multiply a to both sides of an equation. Since we want to multiply a, that's what we're going to do here. We're going to say a times 0 plus 0 equals a times 0. I know I can multiply both sides of an equation by the same number via the multiplication property of equality. So look how I've sneakily incorporated an a into my equation, because I need that a in there. So I've just put it in there by multiplying both sides by it, because I know I can do that. I also know that I can distribute. So a times 0 plus 0 is the same as a times 0 plus a times 0. And that's going to equal a times 0. That's what's on the right hand side. That's the distributive property. Okay. Now, I'm going to do something here that it won't make sense why I'm doing it until we do the next step. I'm going to do it anyway. A plus 0 times a plus 0, so I'm going to leave the left hand side the same. And on the right hand side I'm going to add in 0. I'm going to do 0 plus a times 0. I can do that because I can add 0 to anything and it won't change that. Again, that's the identity property of addition. I can add any number to 0 and it won't change it. So I'm adding a times 0 to 0 and it's not going to change it. The reason I'm doing that is because I'm going to cancel out one set of these a times 0s, this one and this one, and I need something to be on the right hand side of the equation when I'm done. And that something is going to be that 0 that I'm able to add in there. So now I'm going to cancel those blue a times 0s that I highlighted, leaving me with just a times 0 equals 0, which you'll notice is what we wanted to prove. And the reason I can cancel those is what we proved in example number 1, the cancellation property of addition. If I have the same thing on both sides, I can subtract it away, cancel it out. So now I've proven one of the things I wanted to prove, that a times 0 equals 0. The other thing I wanted to prove was that 0 times a equals 0. So do I have to do this whole thing again to prove that? No. Because I know that multiplication is commutative. So if a times 0 equals 0, then 0 times a equals 0. I can commute the left-hand side. The commutative property of multiplication. And now I've proven the other thing I wanted to prove. That example allows us to prove this very, 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 very important property that we will need later on in this course, the zero product property. For all real numbers a and b, ab equals 0 if and only if a equals 0 or b equals 0. Remember, the words if and only if indicate that it's a biconditional. That means we can go in either direction. So if ab equals 0, then a equals 0 or b equals 0. So if two things multiplied together equals 0, then one of those or both of them needs to be 0. Or we can go the other direction. If a equals 0 or b equals 0, then a times b must be 0. That is going to be crucial in order to be able to solve any quadratic equation. We're not going to prove it here, but it follows from the example we just did. One last example, example number 3. If a is a real number and a is not 0, then a squared is greater than 0. If I take any number, positive or negative, but not 0, and I square it, I get a positive number, is what this is saying. Again, something we've generally understood to be true, but let's see why it's true. So we'll start with a real number a. A is a real number. And it's specifically not 0. A is not equal to 0. Okay, and that's what we're given. Number 2. Since a is not equal to 0, there's only two possibilities. Either a is less than 0 or a is greater than 0. How do we know that those are the only two possibilities left? Well, that was from the comparison property, one of our properties of order. That if you have two real numbers, there's only three possibilities. Either they're equal, or one is less than the second one, or the first one is greater than the second one. So we've eliminated at number 1 the fact that they're equal, so a must be less than 0 or a must be greater than 0. So that gives us two possibilities. And we're going to call them case 1 and case 2. Case 1. A is, let's start with a is greater than 0. Okay, if a is greater than 0, what can we do? Well, I can multiply both sides of the inequality by the same number. I can say a times a is greater than a times 0. How can I multiply both sides of an inequality by the same number? That's the multiplication property of order. And I can multiply both sides of the inequality by a positive number. A is a positive number because that's our case 1. And it's not going to change the sign because I know it's positive. And thus, a times a is a squared. And that is greater than, well, a times 0 is 0. And we now know that because of the multiplicative property of 0. We just proved that earlier in the video. A times 0 is 0. Okay, we've shown what we wanted to prove for case 1. So now we need to do it again for case 2. What if instead of a being greater than 0, a is less than 0? Okay, well, we can still multiply both sides by a, but when we do that, we have to switch the sign. And this is why we needed two cases, because they work differently. If a is negative, we end up switching the sign. What tells us that happens? The multiplication property of 0. The multiplication property of order. I'm sorry. If we multiply by a positive number, it does not switch the sign. If we multiply by a negative number, it does switch the sign. That's all this is telling us. And number 6, a times a is still a squared, and that is greater than, well, a times 0 is still 0 for the same reason. The multiplicative property of 0. So notice, the only reason we got a squared is greater than 0 for both cases is because of the fact that when we multiply by a negative number, it switches the sign. Otherwise, we would have ended up with a squared was less than 0 if we hadn't switched that sign. So we got what we wanted to show in both cases. So we have finished our proof. Now your immediate practice problems. As promised, your immediate practice problem is to prove the cancellation property of multiplication, which is written there on your screen. And a huge hint, do not freak out that I'm making you prove something on your own. The proof is highly, highly similar to the proof of example number 1, which was the cancellation property of addition. In order to do that, we added a negative number to both sides. Well, in order to undo this multiplication, we're going to multiply both sides by the reciprocal of c, 1 over c. You know you can multiply both sides by the same number, so make it 1 over c, and then cancel. That is the end of sections 2.6 and 2.7.